Okay, last video. I don't know about you, but I'm kind of happy about that. So we're going to talk about mechanism, okay? When reactions occur, they can occur in a single step where two particles collide with each other with enough energy in the correct orientation and just sort of miraculously form products. Generally speaking, that doesn't usually happen. Okay, so what we do instead is we write a reaction mechanism. And what it happens is the reaction happens in a series of steps. Okay, so the reactants form some intermediate and then a second intermediate and maybe a third intermediate, and they finally get around to forming products. But they happen in 2 or 3 or 4 steps. Okay, one of these steps will always be the slow or rate determining step. Okay. Okay, so whichever one is slowest is the rate determining step. I mean, that makes sense, right? If you're running a race and you run really, really fast and the next guy runs really, really fast and the third guy walks really slowly, they kind of determine how well you're going to do in that race. So rate determining steps tend to be the ones with the most bond breaking and forming. Okay, so the mechanism is a series of steps. It can be a single step that sort of describes what's really happening. Okay, for example, if we look at this reaction where CO reacts with NO2 to give NO plus CO2, when you're at high temperatures, this actually occurs in a single step. Carbon monoxide collides with nitrogen dioxide and forms products. Okay, so do you remember back when I told you that when you want to write the rate law that you cannot use the coefficients from the equation? Well, you still can't, but if you know which step is the slowest, and since there's only one step here, you can. So you can use the coefficients from the rate determining or slow step to write your rate law. So when we write the rate law, remember rate is K times the concentration of the reactants, okay, to some power. So CO is going to be to the 1 power, and NO2 is going to be the 1 power. Remember, you can only do this if you're looking at mechanisms and you know the slow step. You can't do it automatically from the overall stoichiometry. But that comes in handy when you do. Okay? So when you do the same exact reaction though, okay, that CO plus NO2 gives you NO plus CO2, if you do it at lower temperatures, something different happens. It actually happens in a series of 2 steps. An NO2 molecule collides with a second NO2 molecule and makes an intermediate, NO3 and NO, okay? And then the carbon monoxide molecule comes around and collides with this NO3, which I just called an intermediate, we'll see why in a minute, to make the final CO2 plus NO. Now, for a mechanism to be legit, all this has to add up to give us the overall reaction. Okay, so I've got an NO here and an NO2 here, 2 NO2s and 1 over there, so I'm going to have NO2 here. Okay, plus CO, NO3 on both sides, so they're going to cancel each other out, and I'm going to have CO2 plus NO. So when I add those 2 reactions up, you'll see that you get the actual reaction that you were doing. But now we know the slow step. So we look at just the slow step, and we can say rate equals K times the concentration of NO2. But look, there's 2 of them. Okay, that's the same as 2 NO2. So the rate law is rate equals K times NO2 squared. Okay, this is actually the rate law for this reaction when it happens at lower temperatures. It happens in a 2-step mechanism. When you have a substance that appears as a product but then disappears and does not appear in the overall stoichiometry, it's called an intermediate. Okay? It appears and disappears, but it doesn't stick around. Okay? It's important to recognize intermediates because you cannot have them in your rate law. All right? In this case, it didn't matter. We got our rate law without it, and no problem. Okay? So we're going to do another example where we run into a little trouble with our silly intermediate. So let's look at this reaction. This is a two-step mechanism, okay, where NO combines with Cl2 in an equilibrium reaction, okay, to make NoCl2. That's a fast step. And then the NoCl2 reacts with NO to make 2NoCl. So the overall stoichiometry here is going to be 2NO plus Cl2. This is on both sides, so it's going to cross out, it's going to disappear. Gives me 2NoCl. Okay, so that's the overall reaction. And what's the intermediate? Well, the intermediate is NoCl2. So the first thing I do is I look at my slow step, and I go to write my rate law. So rate is K times NoCl2 times NO. Which you'd be like, woohoo, I'm all done. Except you can't do it this. This is cheating. You cannot have an intermediate in your rate law. So what you have to do is get rid of it. Okay? Well, what you're going to have when you need to get rid of it is an equilibrium reaction. So really we're going to talk about equilibrium next chapter. But equilibrium means the forward reaction is occurring and the reverse reaction is occurring. And most importantly, they're occurring at the same rate. Okay? So this forward reaction has a K, we'll call it Kf for forward, and the reverse reaction has a K, we'll call it Kr for reverse. So I'm going to say that the rate of the forward reaction equals the rate of the reverse reaction, and I'm going to write rate laws. So for the forward reaction, it is Kf times NO times Cl2. And that equals the rate for the reverse reaction, so that's Kr times NoCl2. Because if the reaction were going backwards, like that, then that would be my reactant. Okay? So what I'm going to do now is solve for NoCl2. So that's going to be Kf times NO times Cl2 over Kr. Okay, so now I'm going to take this whole thing right here and I'm going to plug it in for that, okay, because it's equal to that. So I'm going to plug it into this equation right there. So I end up with rate is K times Kf over Kr, okay, NO, Cl2, and the NO from up there. Okay. Well, all of these K's, we're just going to put them all together and call them the rate law constant. So rate equals K times NO, there's two of them, squared, times Cl2. So now you have your rate law, and you got rid of your intermediate. So you'll do that a few more times, but the trick to having an equilibrium reaction is that you can use it to get rid of an intermediate. Okay? And this whole spiel I did right here with all of these K's, there's a little bit of a shortcut, okay? So let's see if I can explain that to you before we go off here. If I look at this reaction, if I take the reactants and multiply them, NO times Cl2, and then set them equal to the products multiplied by themselves, okay, I get a relationship that I can plug in to there. Alright, there's a little shortcut. You can remove all the K's. If that didn't make sense, I can show you that later, or you can do it out the long way. But basically we're just saying that they're equal to each other because their rates are equal. Right, so that's mechanism, and the chapter is over.